Hey there, everyone. Welcome to another episode of HET. So, a little while ago, I posted a link to a video on the social media page about a guy who had a really good explanation of how diodes work and why it's important that we connect the polarity correctly on the LEDs when we install them into our headlights. But if you're like me, I'm a mechanical engineer, so to me, anything electrical is basically magic. I'm guessing a lot of you also don't really have a great idea of how electricity works. So I thought I might make a little video series on some of the basics of electricity and how it works. So the key thing to remember is it all boils down to our friend, the humble electron. He has a charge of negative 1.6 times 10 to the negative 19th coulombs. So what is a coulomb, you might ask? So this is basically just the units that we use to describe charge. We write it out as C. And an electron, or its friend, the proton, switch to red here, P, proton. They are the fundamental units of charge, and they both have a charge of 1.6 times 10 to the negative 19th coulombs, but the difference being that the electron is negative, the proton is positive. Okay, so now that we have that understood, we'll kind of go into how atoms work. So if we take an electron and a proton, throw in some neutrons for good measure. So we'll draw a proton here. Give it a buddy neutron. Neutrons don't have any charge. Then our little electrons over here. We have the basic structure of an atom. So this over here, with only one proton would be a hydrogen atom. You can see here, this would be our nucleus, however you want to say it. And then this is kind of the trajectory that our electron would take. So we could add another electron here and make this thing an ion. An ion just means that it has, a non-neutral charge. So if we take this electron out of the equation, this is just a regular hydrogen atom. It has one electron, one proton. The charges of the two cancel, so it effectively has zero charge. Well, let's say by sorcery or somehow we add another electron, and it's spinning around the other way. This would then be a negatively charged hydrogen ion. Similarly, if we were to just blow off these guys here, this would then turn into a positive hydrogen ion, since the positive charge is the only thing that's left. Okay, so now that we kind of know what the basic fundamental charges are, how does that relate to electricity? So one of the fundamental laws about electricity is going to be Coulomb's law, that states that the force between any two charges, or the magnitude of the force, I should say, so we're going to take direction out of the equation, is equal to Coulomb's constant. He discovered it, so he gets the name constant. And this is equal to 9 times 10 to the 9th, approximately, newtons times meters squared times coulombs to the negative second. And again, that's Coulomb's constant. Okay, so it's equal to his constant times the product of the two charges, Q1 and Q2. Doesn't matter what kind of charge they are, positive or negative, divided by the distance between the charge centers squared. So here R is equal to the distance between the centers of charge. Centers of charge. Beautiful. We're moving. Okay. So let's say that we have two electrons. It could be an electron and a proton. It could be two protons. Doesn't really matter. In this case, we got two electrons. So we got one electron over here, one electron over here. And we're going to say that they're separated by a distance of R equals 0.5 meters. That is the distance between their centers of charge. So the forces that each of these electrons feel is going to be equal and opposite. So we got here, this is the charge felt by this electron, F1, and so this electron feels an equal and opposite charge, F2. So F1 plus F2 equals 0, because they cancel. Okay. So with Coulomb's law, we can calculate the force that each of these electrons feel, which is going to be equal to Coulomb's constant. So it's going to be 9 times 10 to the 9th newtons times meters squared times coulombs to the negative second, times the two charges. So we got two electrons. Each of them is negative 1.6 times 10 to the negative 19th coulombs. We're just going to square this because we have two of them. So we got Coulomb squared all over 0.5 meters squared. So these meters are going to cancel. Coulombs are going to cancel. So all we got left is newtons. And that is going to end up as 9.216 times 10 to the negative 28 newtons. So pretty small force, but these are really small particles and they're pretty far away, relatively speaking. All right, so with that, that'll conclude this episode. The next episode, we'll kind of talk about the fields that these charges produce, and how to calculate the strength of those fields at any given point. Thanks for watching. Like and subscribe. Now, I feel like this video wouldn't be complete without a static electricity experiment. So for this, I'm going to have a plastic Tupperware container. The reason I'm using plastic is an insulator. So any charges that I give to it, like rubbing it on my noggin, all of those electrons are basically just going to stick to it. And because it doesn't conduct, there's no way for those electrons to spread out. So they're just going to kind of sit where they are. Basically just create this huge negative area of charge, which I can then use to attract the foil. Now, I haven't done anything to the foil, but because the foil is so thin, all of the electrons are being forced to the other side of the foil, leaving only the positive particles exposed. So this kind of naturally creates a charge differential within the foil, so that all the positive charges on one side, all of the negatives on the other side. The positive charges in the foil are attracted to the negative charges on the Tupperware, and then we have this experiment.